Hello everyone and welcome. In this video, I will be going over the Baseline Robust Aircraft Testing or BRAT framework demonstration. This framework primarily includes a Simulink diagram set up with PX4 input and output, useful for custom algorithm development and validation on UAV platforms that use PX4 autopilots. This Simulink diagram and its subsystems may require modification depending on your use case. This video is divided into two separate parts. In part 1, I will show you around the BRAT Simulink diagram to show you what is available. In part 2, I will walk through the UAV Toolbox features in Simulink and how they can help you interface with your PX4 autopilot. This is the BRAT hardware deployment model. You'll see three main subsystems. FCS throughout the diagram stands for Flight Control System. So we see FCS inputs, FCS, which is where our main control logic is going to be, and then FCS outputs, which is how we actually write back to the board. I have everything here in a slide deck so that I can use the laser pointer, but this is how it'll look for you inside of Simulink. First, we're going to go inside FCS inputs. So if we click in there, we'll see four subsystems here. So we have read ARM, read RC, read PX4 sensors, and read PX4 params. So they're pretty self-explanatory. We're reading in the arming signal from PX4, reading in signals from our transmitter, from the PX4 sensor suite, and then PX4 parameters. So going inside the arming subsystem first, here, all that's happening is we read in the signal from PX4 ARM, and then we check it against if our pilot switch is turned into the armed position. So all that means is that we both want the actual state of the vehicle from PX4 to be armed and for our arm switch to be set correctly in here, and then the arm signal will go out throughout the subsystem. This is for safety, just so that we don't have an ARM switch set inside our Simulink logic that differs from PX4 logic, and we don't have an issue that would normally stop the vehicle from arming be ignored by our logic. So this just reads in the PX4 signal so that there aren't any issues with that. So going back out, next we'll click into the RC subsystem. So we see here we're reading in from a UORB topic called RC channels. So that will read in all the channels coming from our transmitter. In this case, the tags are labeled based on the switches, sticks, and knobs from the Spectrum IX20. From there, we take those stick commands. They're normalized between -1 and 1, so we pass them into the sticks tag. These other switches, we map the PX4. If it's a 3-level switch, for example, it'll be -1, 0, and 1. So we map those into the same numbers that we see on the transmitter. And then those numbers are sent throughout the diagram. Going back out into our input system, we have the sensor suite. So here we read in all of our state of the vehicle and then some extra information. So we have our standard vehicle attitude and Euler angles, angular rates, position, translational rates. And then we also have some additional tags here read in from different UORB topics from the board. All this is just to get you started. Feel free to add or customize this to suit your needs. Finally, we have a parameter subsystem. This is where we would add any custom parameters that we put into the PX4 code and then read them in here. You can also read in stock parameters, but for my previous use cases, we build custom parameters, maybe to tune gains or to control the amplitudes of inputs, and then we'll put them in the subsystem. So to get you started, I have a custom param1. This corresponds with the custom firmware modification section of my appendix, also available in that GitHub repo, linked in the GitHub repository in the description. So back in the main view of our diagram, we're going to click into the main FCS subsystem. This is set up to have the PX4 control available to you as a fallback, and then have an experimental control block where you can put in your control algorithm. All you need to do is make sure it properly interfaces with the actuator commands. So your controller should use states, whatever other signals, pilot commands, etc., and the output should be mixed actuator commands. So going inside that first block, the PX4 control, all that's happening here is we're reading in from actuator motors and actuator servos. So this is what the PX4 control is inherently doing for the airframe that you select. We're demuxing those signals and then we're putting them back into this vector called actuator commands. So these are normalized signals. We read in actuator motors and actuator servos. These can range from -1 to 1 each, but in our case, the positive rotation of the motor is 0 to 1. So anything below 0 up to -1 would be reversed. So 0 to 1 is read in here for the motors, -1 to 1 is read in for the servos. If your airframe doesn't use all these motors and servos, and more times than not, it will not use them all. All that you'll see in the unused channels are NANDs. Going back out to our diagram, again, we were just in PX4 control. We go into experimental control. This is built for you to plug and play your control algorithm and your mixing algorithm such that you output motor and servo commands in that same normalized fashion that's compatible with PX4. So I've read in some example signals here. Feel free to modify however you need. There's also a data output in case you want to log any of those signals from inside Simulink. I'll talk about how that works in a little bit. Our next block is our control selector. So this is very important to make sure we have the correct transmitter switch selected here such that we can control which control mode we are using. So if you do intend to use PX4 control as a fallback, you would want to ensure that you have the correct switch programmed and that it will switch between PX4 control and your custom control as needed. If you're not doing custom control, go ahead and pass those actuator commands through. You don't need to do any kind of selecting. Our next system is built mostly because of our experience doing program test inputs for system identification. So this is the ability to add on a signal like a frequency sweep, a doublet, a multi-sign injection on top of the actuator command coming out from your controller or from PX4 control in order to do system identification in flight. So again, this is an empty subsystem. Right now, it just passes through those actuator commands unmodified. If you do intend to modify them by injecting an input over top of them, this is where you would do that. So that's it for our subsystem. Again, there's some data tags that flow out through this data port that will be used in our custom logging. Now that we're back in our main diagram, we're going to go to the FCS outputs section. Here we have three main blocks. This first block is where we write the actuator commands back into PX4. I'll explain that in a minute. This subsystem is where we write signals internal to Simulink over a telemetry connection. So I'll explain that. Finally, we see that we can write to the ulog logging structure that PX4 uses to log flight data on an SD card. So I'll explain that as well. The first system we're going into is the send actuator commands. In this subsystem, we use the PWM output blocks to write to our motors and servos. You will use these blocks regardless of if your servos and motors use a PWM protocol, a drone CAN protocol, or some other communication protocol. So how this works is that these blocks actually write to the actuator test UORB topic. These 8 signals in the main version of the PWM output block write to the 8 motors. These 8 signals in the auxiliary PWM output block write to the 8 servos. All that needs to be done in here is writing between 1000 to 2000 for each of these blocks. If you don't use all 8 motors or if you don't use all 8 servos, that's okay. Just leave this logic as is. This will not affect anything in PX4 for those channels or motor numbers that you don't use. To set this up properly, you would go into Q ground control under the actuator tab. You would assign all the required motors and servos for your airframe. And so motor 1 commands will be written to channel 1. Motor 2 commands will be written to channel 2. Same with servos. Servo 1 is written to channel 1. Servo 2 is written to channel 2. These ranges must always be between 1000 to 2000 PWM. So as long as you're sending in that signal properly for servos, which is -1 to 1 and 0 to 1 for motors, this logic will take care of the rest. Back in the main portion of our FCS output subsystem, we have send ground control system data. This subsystem will be renamed to get rid of the fixed wing label just to make this vehicle agnostic. But inside this subsystem, we have 58 available signals that we can write into this vector. So I've left them all blank except for one. Feel free to modify this to suit your needs. In order to activate this debug array coming through on your telemetry connection in Q ground control, you'll need to follow the steps in the hardware setup repository, which is linked in the GitHub. Finally, we have write ulog data. This subsystem is variant. So in the next part of the video, you'll see how to launch this diagram. Whenever you choose the connected I/O setup in the hardware script, this block becomes blank. So all of these signals just go to termination logic. This is because this ulog block inside is not compatible with the connected I/O bench testing mode, but it is compatible when you embed the firmware on the board. So the setup script takes care of switching between those two variants for you. Inside this block, we see the ability to write to a custom UORB message through this ulog block. Setting up the custom UORB message is also explained, linked in the GitHub repository. Right now, I have the example version set up, so this takes 3 attitude signals and 6 control signals. If you modify this UORB message that you're writing to, in this case it's called FCS signals, you will have to go through the hardware setup screens again, and then the next time you open your Simulink diagram and select the correct topic on this block, this will update with all of the signals that you add. Now in part 2, we'll learn how to use the BRAT diagram, interfacing it with PX4, including bench testing and flight testing modes. At this point, if you're following along with this video as a tutorial, make sure that you have your UAV Toolbox support package for PX4 autopilots fully set up before continuing. I'll link my video guide on how to set up the UAV Toolbox below. This setup script called setup hardware will add all of the relevant files to the path and open the BRAT Simulink diagram. When you run this script, you'll be prompted for an input. This input asks if you're going to use the connected I/O bench testing mode or the build, deploy, and start embedded mode. As mentioned earlier in the video, all this does is switch the logging subsystem to a variant where the ulog block is not present. That way we can run the connected I/O mode without issues. You'll still have to start the connected I/O simulation or the build, deploy, and start mode from within Simulink. If this is your first time opening Simulink after setting up that PX4 support package, I'll go ahead and show you how to get this hardware tab to show up. First, go to Model Settings and select the PX4 autopilot that you set up in the hardware setup screens. Once you click OK, it'll initialize the board parameters and the hardware tab will appear. Now that that's out of the way, go ahead and set your stop time to inf or infinity for the connected I/O mode. When you click run, your computer will compile all of the Simulink logic and input and output it while connected to the PX4 autopilot over a USB connection. This is a very useful bench testing mode. Although it's not run in real time, you'll be able to monitor signals throughout the diagram. Sometimes this step takes a while, so I'll speed it up. If you've done the hardware setup screens, this dialog block will look familiar. Go ahead and reboot your autopilot, and the connected mode will begin shortly after. Now that the connected mode is running and my Pixhawk is connected, I'll go into this main diagram to show you one of the signals and how it changes in this mode. As you'll find during your testing, being able to troubleshoot and iterate code this quickly while connected in a bench test environment will prove very useful. Now that we've demonstrated the connected mode, we'll go back to the setup script and get ready to embed the firmware on the board. Now that we're back in Simulink under the hardware tab, click Run on Board and we'll get ready to deploy this as custom firmware. There's also an option to build just the PX4 firmware file, but not deploy it to the autopilot, which can be useful if you send this to another computer. Go ahead and click Build, Deploy, and Start, and the process will begin. I'll speed this part of the video up, but I've personally seen the build, deploy, and start function take between 2 to 15 minutes depending on the device and the amount of custom logic you have built in Simulink. Eventually, the reboot prompt will come up. Go ahead and do that. Once you plug the autopilot back in, Simulink will begin flashing the board with your custom firmware. Once the firmware is flashed successfully to the board, you'll see Ready appear in the bottom left of the screen. Now you can plug your autopilot into Q ground control and go through the PX4 setup process to prepare for flight.